Good morning, everyone. I'm Kim from Seoul National University and Samsung Electronics. Today, I'm going to talk about our practical erase suspension technique for modern low latency SSD. We focus on the erase operation of NAND flash memory to reduce read-tail latency. This is joint work with my colleague at Seoul National University, Samsung, and Sungkyunkwan University. NAND flash-based SSD have become a de facto standard in a data center environment, allowing us superior throughput and low average latency. I'm sorry. As well as low price. It is true that SSDs can achieve very low average latency and superior throughput, but their tail latency remains low. The figure demonstrates this issue with the real low latency SSD. The x-axis represents the percentile of read request, and the y-axis represents the latency with log scale. The low latency SSD using a low latency NAND and a controller shows very low read average latency, which is 160 microseconds. Yet, its tail latency of 5/9 percentile and over is very high. In this paper, our read tail latency goal is sub 200 microseconds, which is competitive with the emerging NVM-based SSD. There are two significant sources of long read tail latency: garbage collection and flag erase operation. Garbage collection induced the read tail latency used to exceed 100 milliseconds. But now, thanks to many advanced garbage collection techniques, the latency has decreased to 10 milliseconds. Therefore, the NAND flag erase operation has become the dominant source of read tail latency. Generally, NAND flash memory cannot execute multiple commands at the same time, so if the NAND is erasing a block, a read request cannot be processed until the erase operation is completed. To solve this problem, the erase suspension scheme has been devised. Now, I'm going to explain how the read latency can vary depending on the state of the NAND. First, if the NAND is idle, an incoming read will have a latency of 30 microseconds. But in a NAND erasing a block, the read latency may be over 10 milliseconds because the read operation cannot be performed until the current erase operation is completed. In contrast, if the NAND supports erase suspension, the ongoing erase operation is immediately preempted by the read command, and thus the latency of read request will become 130 microseconds. As shown in the figure, an existing erase suspension technique can reduce the read tail latency to sub 200 microseconds. Despite such advantages, the original erase suspension scheme can cause write starvation as well as NAND reliability problem. So, we've proposed 3 practical erase suspension techniques that achieve sub 200 microsecond read tail latency without having the problem of write starvation and endurance degradation. The modern NAND flash memories performs the erase operation with multiple discrete pulses, and thus our practical erase suspension technique perform erase suspension on well-aligned safe point. First, the immediate erase suspension technique allows a very low read tail latency by immediately suspending the ongoing erase operation. Next, the deferred erase suspension technique solves the write starvation problem by allowing the current step to progress. Eventually, the timeout-based erase suspension takes the best of both between the immediate erase suspension and deferred erase suspension. Before describing our practical erase suspension technique, let me discuss how the existing erase suspension scheme can cause the write starvation and endurance degradation problems. As shown in the figure, let's suppose the NAND begins erasing a block, and at around 1 millisecond of the process, a read request comes in. And read number 1 was also processed within 130 microseconds thanks to the erase suspension. At this time, however, the erase pulse immediately suspended when read request number 2 comes in. If the read requests are bursty, the remaining erase pulse can never be processed. This means this example shows the erase operation can starve if the read requests continue to come. Erase operations stress NAND flash memory so that the endurance of NAND depends on the number of program and erase cycles. Therefore, the additional erase stresses caused by the erase suspension and resumption also negatively affect the endurance of NAND. And it can overly erase the NAND blocks. Eventually, such overly erased NAND blocks generate uncorrectable read errors, decreasing the endurance of SSDs. So, using incremental step pulse erasing scheme that's called ISP, we've proposed the practical erase suspension technique that does not cause the write starvation and endurance degradation problems. ISP is a standard feature of modern NAND flash memory, gradually applying the higher voltage and minimizing stress on the NAND cells. A single erase step consists of an erase pulse and a verify pulse. An erase pulse extracts the electrons from cells in a NAND block, and a verify pulse detects the NAND cells in a block and decides whether or not to perform the next erase step with the higher voltage. Generally, the modern NAND flash memories are designed to complete the block erase operation within 5 times. From now on, let me talk about how our practical erase suspension can achieve the target performance without side effects. The immediate erase suspension is a practical variant of the original erase suspension. As shown in the figure, the NAND is erasing a block, and a read request incoming. The immediate erase suspension cancels the ongoing erase step within 100 microseconds. And the read request is completed. When resuming erase operation, the immediate erase suspension performs verify operation first. Such verify operation detects the erasing status of the NAND block. Then, if the NAND block has already been erased, the verify operation completes the erase operation without any additional erase pulses to prevent the over-erasure problem. But if there are unerased cells in a NAND block, the immediate erase suspension restarts the previous erase pulse. As a result, unlike the original erase suspension, immediate erase suspension does not cause the endurance degradation of SSD. However, the immediate erase suspension cannot solve the write starvation problem as shown in the figure. The write starvation problem from bursty read request appears in both the original erase suspension and the immediate erase suspension. Now, let's see how the deferred erase suspension technique resolves the write starvation problem. In this scheme, an ongoing erase step is not suspended by an incoming read request. This technique suspends the erase operation only having completed the ongoing erase step. And after the read operation is completed, the erase operation resumed from the next pulse. In other words, the deferred erase suspension prevents the write starvation by ensuring forward progress for the erase operation. However, this technique has longer read tail latency than immediate erase suspension does, although it can solve the write starvation problems. Both immediate erasure suspension and deferred erasure suspension have their own advantages, and we want to have the best of both. So we would like to propose a timeout-based switching mechanism called TES. Timeout-based erasure suspension operates as an immediate erasure suspension mode for timeout value, and if a specific write request does not complete within the timeout, it switches to a deferred erasure suspension mode to avoid write starvation. The timeout value is an effective latency control lock per user. For example, if we set the value to 64 milliseconds and the garbage collection induced write latency is 35 milliseconds, and then the maximum write latency remains under 100 milliseconds. So we evaluated our practical erasure suspension technique with 1 micro benchmark and 2 realistic workloads. The timing parameter of the low latency NAND and SSD controller are used to model our schemes. Furthermore, we had 3 configurations to evaluation for comparison. Here is the FIO random test result. This micro benchmark generates a random per kilobyte request with 70% of read, 30% write, and 16 outstanding requests. Regarding read tail latency, the tail latency of baseline is as long as 5 milliseconds, which is an entire erasure operation. And deferred erasure suspension shows 1 millisecond of tail latency, which is single erasure pulse latency. Immediate erasure suspension and timeout-based erasure suspension make possible sub 200 microseconds of read tail latency by canceling the ongoing erasure pulses. Conversely, the write latency of immediate erasure suspension and timeout-based erasure suspension tends to be longer because such a scheme avoids the erasure pulse multiple times. For database benchmark, we use Aerospike certification tool called ACT. As shown in the above table, ACT consists of 3 threads. Each thread generates its own request according to predefined rate. ACT has 2 evaluation criteria, performance test and stress test. As shown in the table, the SSD number 1 is certificated for 2x multiplier, and the SSD number 2 is for 8x multiplier, which means that the SSD number 2 can do 4 times as much work as SSD number 1 can. Here is ACT result. The baseline passed only 14x multiplier because of long read tail latency. The original erasure suspension and the immediate erasure suspension suffered from the write starvation problem, so they did not finish their 30x multiplier. The figure shows the tail latency as 13x multiplier. The deferred erasure suspension and timeout-based erasure suspension shows the best result for both stress test and performance test. Finally, we use Tpcc Benchmark to evaluate our practical erasure suspension technique. As for the read tail latency, the baseline and the deferred erasure suspension, they are both bound to their own characteristic, which is an entire erasure operation for the baseline and a single erasure pulse for the deferred erasure suspension. The original erasure suspension and the immediate erasure suspension also did not finish the test because of the write command timeout. The timeout-based erasure suspension shows a similar read tail latency trend to that of the deferred erasure suspension. It means that the timeout has been triggered to switch to the deferred erasure suspension mode. Based on the read tail latency behavior of timeout-based erasure suspension, its write tail latency can be predicted. For example, the 88 millisecond write tail latency consists of 2 sections. First, for a timeout value of 64 milliseconds, the timeout-based erasure suspension was operating in immediate erasure suspension mode while canceling the ongoing erasure steps. Second, after the timeout is triggered by the pending write, delay suspension mode switch to deferred delay suspension mode. And the SSD performs the garbage collection operation for user's write request. In other words, although the write tail latency of timeout-based delay suspension is getting longer, it's deterministic, and it can simply be controlled by the timeout value. In summary, we propose practical delay suspension techniques, minimizing the impact of erasure operation on read tail latency, and achieving very low read tail latency without write starvation and endurance degradation. So, we believe these schemes harness the full potential of NAND flash-based SSD. This is the end of my talk, and thank you for your attention.
Thank you very much. This is a problem that it's very good that someone finally solved.
Thank you.
I'm specifically interested in the timeout and setting the timeout. Who is supposed to determine what the timeout is?
Mm-hmm. We have performed a sensitivity test for the timeout value, so I would like to show some slide. Generally, increasing TS timeout value n lowers frequency of high latency read and decreases average read latency. However, it increases the maximum write latency, but the longer write latency is deterministic.
That's a very nice trade-off. So this is for the application to determine what the latency should be?
Yeah. Currently, it is a static value. However, we believe it's controlled dynamic fashion using NVMe special command. For example, Tpcc command, it can control SSD function, and NVMe IO reserved field, which can control the command-based fashion.
That's very nice. Okay, thank you very much. Oh, one more question?
Yes. So actually set by the user or the system admin, but it's based on one factor you need to consider is what's the maximum target maximum write latency. So if you actually have, for example, if your maximum target latency is like 100 microsecond, then you set the value for example, set to like a 64, then you know the sum of this like n value plus the maximum GC induced write latency will be roughly the same number with the maximum target write latency.
So it's totally controlled.
Of guideline.
Right. Thank you. Thank the speaker again.
Okay.